Hello everyone. Our this discussion for today is basically that we will explore more about the experimental evidences, and we were talking about the factors which influence the SN1 mechanism and SN2 mechanism. From the previous discussions, we have seen that what are basically the SN1 kind of reaction mechanism and what is the SN2 mechanism. And we also have discussed the list of the factors which influence what is the SN1 mechanism and what is the SN2 mechanism, and if this is a nucleophilic substitution reaction. So what are the preferences that when this itinerary or when this is route is obtained, SN1 mechanism or SN2 mechanism. So just for your reference and just to refresh that what we have discussed in the list of the factors, or you can say the experimental evidences which has proven that these are the factors or these are the parameters on which the SN1 mechanism and SN2 mechanism depends. So these are kinetics, stereochemistry, structure of the haloalkane, structure of the leaving group, solvent do affect the pathway, that either that has to prefer the SN1 or that has to go for via SN2 mechanism. Then the structure of the nucleophile, and last one is the skeletal rearrangement. Another fact which we have established from this discussion is that we have seen the two extremes. One was the tertiary haloalkane, another one is the methyl haloalkane, and that is also the fact which has established and proven by the experimental evidences that tertiary is always preferring the SN1 mechanism because that is able to form the stable carbocation, while the methyl haloalkane will go for the SN2 mechanism because SN2 mechanism is that mechanism in which the nucleophile and haloalkane, they both are in the rate determining step. So there is no true carbocation formation as a stable intermediate. So they both events are happening at the same time. So they prefer the mechanism or the pathway via the SN2 mechanism. So our today's discussion is basically about the structure of the leaving group and the structure of the nucleophile. So the both are very important, and today we will see that what are the criteria or what are the preferences and what we have to see and compare and analyze, that what kind of structure of the leaving group is favoring the SN1 mechanism or SN2 mechanism, and what is this we have to see about the structure of the nucleophile. So let's start firstly about the leaving group, so that you all know that what the leaving group is. So this is basically that part in the nucleophilic substitution reaction that which will break the bond between with the carbon, and finally that will eliminate and that will be substituted by the nucleophile. So another fact is this one, that when this leaving group is leaving the haloalkane, which is initially or reactant or the starting material, so they eliminate in the form of the ions. So again, they are also rich in electron. So these are kind of nucleophile, but we in our discussion we separately designate it as a leaving group because this is leaving that system, and the nucleophile because this is more rich in electron, they have more power to kick off that leaving group. So that's why do keep in mind that leaving group is also these are in the leaving the system in the form of the anion, and they have the negative charge or they are rich in electron, but they are not as powerful as the that competing nucleophile which is able to kick off that leaving group from the system, because these negative or negatively charged ions, or these radicals or the ionized forms are basically more stable as a leaving group. So they are the good leaving group. So we will see what are the good leaving groups, what are the bad leaving groups or the weak leaving groups. So why we are talking about these one, right? So basically, the leaving group develops a partial negative charge in both Sn1 and Sn2 reactions. So we have seen in the reactions what was happening, that if there was a methyl bromide, so let me write that one for you. So for example, if this was the methyl bromide initially, right? So when that bond is breaking, so what is happening? Because we have seen so far the example of the leaving group as the halides one. So they have the high electronegativity, and they have the tendency, they have the potential to pull off that electron pair towards itself. So that's why they get negative charge, and while making this partially positive one. So what happened in case of the tertiary one, that this is fully cleaved, that bond is completely broken, and then we have the carbocation. But if we are talking about Sn2 mechanism, so this was happening at the same time. So this is not completely broken unless there is attack of a nucleophile too, right? And then this reaction will happen simultaneously. So the most stable anion and therefore the best leaving group are weak conjugate bases of strong acid. So that is another thing which we know from basic information about the acids and bases and how they break, how they ionize in the system. So if you want to refer and you refresh this concept and information, so do check my videos on the acids and bases. So what happened is that when there are some of the carboxylic acids, so they do ionize in the form of that every acid is ionized in the form of the negative and the positive charge. So the ionized forms are referred to as the conjugate bases, because these bases are basically developing in the system, and they have originated from certain kind of strong acids. So if the acid was strong, initial acid was strong, and after ionization they are creating the conjugate base which will be weak in return. So weak conjugate bases are usually the good leaving group. So that you have to keep in your mind. So if you just look at this figure, so this is also giving you the clear idea, and you have to see that what is the trend of the leaving group. So reactivity as a leaving group it is increasing from right side to the left, and the stability of anion, strength of conjugate acid is again increasing towards the left side. So what does it mean? That the stability of anion, the most stable anion, and the weak conjugate base is basically the good leaving group, right? So this is the acid, it is the weak acid, and as we are increasing, as we are moving from towards the left side, so the strength of the conjugate acid is increasing while the base is getting weaker, right? So, for example, to your understanding, I would say that ammonia is basically the weak acid, and you have probably more heard about the ammonia as more of the basic side. And while the HBr, hydrogen bromide, hydrogen chloride, or hydrogen iodide, they are the most stronger acids, right? So, the stronger acids ionize to give the weaker conjugate base, and this weaker conjugate base can stable in the system for a certain time, right? And they can stay, so that is a good living group. While the weaker the stronger conjugate bases are basically more into that they are stronger enough, they are reactive enough, and they are looking for the proton part, and they just wanted to complete their self, right? So their ionized form is not as stable as these one. So the stronger anions are basically the good, you can say the leaving group, because they can stay in the system, and they are the stabilized forms. So now that was about the leaving group, and now we will talk about the nucleophile. So nucleophile has more concern when we are talking about the nucleophilic substitution. So we will talk more about the nucleophile. So nucleophilicity is basically the strength, you can say, or that is a potential, that is its power to substitute, how fastly or how strongly it substitute the living group, right? So if a nucleophile is very much reactive, and this is very faster, and it has a very high rate of substitution, so that has a high nucleophilicity. So this is a kinetic property because this is dependence on the rate of the reaction or rate of the concentration of something. So if you are measuring that one by the rate at which a nucleophile causes nucleophilic substitution on a reference compound, which is or haloalkane, under a standardized set of experimental conditions. So we have set the temperature, we have set the solvent, and what are the stoichiometric values, like how many grams or moles we are taking. So then it is depending on the nucleophile and its nucleophilicity. So for this reaction, if we compare that one, so what is happening? So this is the ethyl bromide or bromoethane, and there is the ammonia, which is a nucleophile, and we are comparing that what is the rate of this nucleophile to substitute this bromide with NH2, right? So here this reaction is happening in the ethanol at 25 degrees C, means this is happening at a room temperature, so we are not heating that one. So here, this is the nucleophilic substitution, and obviously later that extra hydrogen will remove, and this will be the CH3, CH2, NH2, and that will be ethane, aminoethane or ethylamine, right? So that is or one kind of nucleophilic substitution reaction. So now we have to see that this nucleophile is basically responsible to give you the idea that what is the class of the compound you are forming. So for example, when we were talking the hydroxyl OH negative, so we were able to form the alcohols there. When we were talking taking any of the longer chain of the alcohol one, or we are using any of the alcohols like the methanol or the ethanol as a solvent and as a nucleophile, so then we were creating the ether here, right? So this nucleophile rate and how it is easier for this nucleophile to substitute that one at a certain time. So this is basically the nucleophilicity of the nucleophile. So now refer to this table. This is basically giving you the idea, the most common nucleophile which we are talking about in this course, and what are the general classification of a nucleophile. So on the basis of their effectiveness or on the basis of their nucleophilicity, right, in of the nucleophile, they are classified or they are grouped in the three major, you can say the ranges, three major groups. So one is the poor nucleophile, moderate nucleophile, and the good nucleophile, right? So firstly, we will see at the bottom, this is the poor group of the nucleophile. And if you just look at this one, there is the water, there is methanol, there is any of the alcohols, and there is the acetic acid, there any carboxylic acid. So one thing is important, that they are in a neutral form, means they are not ionized. These are not the anion form. So they are the fully protonated forms of these one, and they are grouped as a poor nucleophiles because they have the least nucleophilicity in comparison to other of the nucleophile, right? So then we move on to the moderate class of the nucleophile. So once this acetic acid and this carboxylic acid get ionized and they are in their anion form, right? So they have gradually lifted, or they have enhanced their, or there is an increase in their nucleophilicity. So they comes from poor to the moderate one. Then all of the thiol and the sulfide groups are also in the moderate class. Then the nitrogen containing nucleophiles, which are again in their fully protonated form, so they are in the moderate group. Then there is the Cl negative and F negative. This is a chloride and the fluoride ion. So they are in the moderate group. Well, I will more talk about this chloride nucleophiles later. So then lastly, there is a good class of the nucleophile. So here all kind of anions, especially the cyano, azides, and amino, then hydroxyl, then methoxy, alkoxy, any of the alkyne. Then there is the ionized form of these thiol compounds. Then this is the again the sulfide compounds in the ionized forms and the Br negative and I negative. So these are grouped under the strong or the good nucleophile, right? So an interesting thing you may have observed there, the halides one or the halogen, so two members of this are grouped in a moderate, while these two are grouped in the good one. So if you just look at the group downside in the periodic table of the halogen one, which starts from the fluorine, then chlorine, then bromine, and then the iodine one. So from fluorine to the iodine down the group, we are basically facing there is the decrease in electronegativity and there is increase in the size. So once the size of the halide is increasing, so there is the increase in the polarizability or the charge polarization because they are the bigger in size. So they have the more charge distribution. So let me give you the example. So for example, this is the bigger picture of one of the iodine, and this is the fluorine, which is very tiny in size in comparison to the BRCl, right? So when there is a negative charge, because once this is pulling off that electrons towards itself, so this is getting the negative charge, and there will be another atom, the carbon or something, which is having the positive charge, right? So there is a certain polarization of the charge. And obviously, this is very tiny, so that doesn't get beyond to that one. Once we compare the iodine with that one, so here in iodine case, what we experience that this is a negative charge and there is a huge volume where it can do exist right around this one, and this is negative, and there will again the positive partial positive side where this is the side from which it is pulling off that electron pairs towards itself, right? So it means there is a more charge distribution, there is more polarization, so that is able to work on with the other positive side. So this is having the huge gap, right? So this polarization is also increasing the nucleophilicity of the reactions, right? So there are multiple things which we have to consider about the nucleophile. So we are talking later. So on the basis of the size and polarization, so the Cl and F, they are smaller as compared to the Br and iodine, iodide one. So they are in the moderate, and while the Br negative and iodide are at the top group, which are termed as the good nucleophile. So now the basicity and a nucleophilicity, we have discussed previously that the nucleophiles are also termed as a Lewis basis, and another definition of the acid is any species which is able to form the bond with the hydrogens due to their lone pair of electrons. So these are also termed as the Bronsted bases. So the nucleophile, all of the nucleophiles are basically the Bronsted bases as well. So there is a correlation between nucleophilicity and basicity. So whenever you are talking about the nucleophilicity, so there will automatically, there is a term, the basicity would do exist, and their basicity values we have to analyze and we have to take in account before analyzing overall that this reaction is happening through the Sn1 mechanism or Sn2 mechanism. So basicity and nucleophilicity are often related because they both involve a lone pair of electrons making a bond to another atom. So when we talk about the base, so this is preferably making that bond with the proton. And while we are talking about the nucleophile, so again, this lone pair is basically making a bond, but here the priority is not only the proton, so that can make a bond preferably with any of the electrophilic carbon, which is getting deficient an electron and which is carrying the positive charge. So in general, sterically unhindered strong bases are good nucleophile, right? So sterically unhindered means that the structure is not fully crowded one. So for example, there could be the structure of the tertiary butyl, right? And, and this is the structure, or there could be the simple, this one, or I can write the Cl or the Br1. So once this is with the negative charge, right? So that has to be, this is a negative charge or this is the negative charge, right? So this is the side which is crowded one. So that is sterically hindered. So it has the limitation that it can only work up or the move or making a reaction or bond from only the one side, because this is crowded or its window is closed, just like we have discussed that pattern with the tertiary haloalkanes and the primary. We have compared that one, right? So the next thing is, there are some key trends in nucleophile, and if you will go through all these and you keep in your mind, so that will make your life easier about the synthetic and organic chemistry, that what you have to look into nucleophile and what is probably going through the SN1 or SN2 mechanism. While one important thing about today's discussion is that first thing, which initially I have mentioned, that the tertiary haloalkanes are always going through the SN1 mechanism, while the primary and the methyl, they always have the preference towards the SN2 mechanism. There is the center line, or there is the intermedian, which is the secondary haloalkane. So they then have to decide that they have to opt the SN1 mechanism or through the SN2 mechanism. So then they are the deciding factors, that what are your solvent, what is your nucleophile structure, which is a leaving group, what is the haloalkane originally, right? So then analyzing all of these factors, we are able to pick up and we are able to predict that this reaction is happening through the SN1 or SN2 mechanism. So just keep in mind some of the key trends, or you can say these are the hacks to remember that oxygen anions such as the hydroxide and methoxide are good nucleophile because they are also strong bases, right? So this is on the basis of the anion, and the straightforward thing about the some of the nucleophile, if they are oxygen carrying and they are anion one, so they are straightforwardly the good nucleophile because they are the strong bases as well. Weaker oxygen bases are similarly weaker nucleophile. So here the example is the carboxylates, ionized form of the carboxylate sites, and you have seen that this was placed in the moderate, right? While these are in the good one, right? Are classified as moderate nucleophile. Then anionic atoms are more nucleophilic than their neutral counterparts. So we have seen then when the carboxylate is in its fully protonated form, and this was in a neutral form, so that was grouped in the poor nucleophile, and when it gets ionized, so this is in the moderate one. And here we also have seen the thio and the sulfide groups with when they were in the form of SH, so they were in the moderate, and then when they get up in the ionized form, so they were grouped into the good nucleophile group. Now, from these state forward facts, there are some of the example of the carboxylic acids or some of the more complex molecules for which this is not simple thing that they are in an anion form, and they have to be stronger bases or the weaker nucleophile or the stronger nucleophile. So then we have to keep check their value of the pKs. So every molecule when it gets dissociate and the acids, right? So they have certain value of dissociation constant, that it is giving proton and this is having another negative counterpart part of that molecule. So we will check its pK's value, and that is easily available in the literature. So either if the pK value is above 11, so we categorize this as a strong nucleophile because they are the through the conjugate acids, which then forming and dissociating to generate the weak basis, conjugate basis, and then the proton one. So if the pK value is above the 11, so that is termed as a stronger nucleophile. If this is around 11, so these are as a moderate nucleophile. And if they that fall below the 11, so that these are the weak nucleophile. All other factors being equal, the stronger the interactions of the nucleophile with the solvent, the lower is its nucleophilicity. So if a nucleophile is more interested in a solvent rather than in the haloalkane, so it means that is losing its nucleophilicity, because now this is solvated by the solvent and this is not readily available for the substitution of that leaving group with itself. So the solvents are also deciding that the nucleophilicity or the nucleophilic character of the nucleophile is how this is predominating. So there are the two kinds of organic solvents, aprotic solvents and the protic solvents. So the in a aprotic solvents, which the aprotic solvents are those solvents which are not able to give the hydrogen to the system. For example, the DMF, for example, the acetone, these are the aprotic solvents, right? So anions are only weakly solvated because this is not giving that H positive. So this is not solvated that much while with the solvent. So they are readily available for the nucleophilic substitution reaction, right? So if the aprotic solvent is in your system, you are conducting your reaction in aprotic solvents, polar aprotic solvents, so then the basicity will dictate the nucleophilicity. So it means the basicity is basically the deciding factor that your nucleophile is stronger one or the weaker one. So higher or the stronger the base, so it is the more stronger nucleophile if this reaction is happening in the polar aprotic solvents. So that is very important to keep in your mind. So if we are conducting a reaction, nucleophilic substitution reaction in a polar protic solvents like the methanol, ethanol, or the water, so anions are highly solvated by the hydrogen bond with solvent molecules and therefore are less free to participate in nucleophilic substitution reaction. So then its basicity is the factor which gets lower because it is already well solvated with the solvent molecule. So now there is the polarizability, which will dictate that this nucleophile is stronger one or the weaker one. So polarizability is the charge distribution. Now these factors are basically the more predominant in case of our halide nucleophile, right? So right now we will focus our discussion on the halide nucleophile because that trend is more promising and predominant in the halides. One rest are their pK values, their basicity. So these are the other factor, their steric hindrance, their structure is important. So if the polar aprotic solvent is there, so then you have to remember the increasing order of the nucleophilicity of the halides, that in polar aprotic solvents, so your most stronger nucleophile is the fluoride one, because this is the weakest conjugate base and it comes out from the stronger acid HF, and this is very small in size. This is highly electronegative, right? So in polar aprotic solvent, where the hydrogen is not present or contributed to the solvent, they are not well solvated. So then even with the teeny size and with a very stronger base, so that fluoride is basically predominating as a nucleophile, right? Now, the polar protic solvents. So in the polar protic solvents, the fluoride is basically at the least, and iodide will predominate because of the high polarizability, right? Because of their high size, bigger in size, and there's the most and the highest charge distribution, highest polarization value. So if we compare the both extreme, the fluorine and then the iodine one, so the fluoride is the having the highest basicity value, right? It means its pK value is above 11, and iodide is having the higher polarizability value. So you have to see that the in a polar aprotic solvents, the basicity predominate, and in the polar protic solvents, so the polarizability predominates, right? Now at the end there is a task, and from this task I have given you the two questions and the two pairs. So from each pair you have to pick the stronger nucleophile, and you have to justify your answer, that why you have categorized, or you have stated that this is a more stronger nucleophile rather than the other part of this one. So then you just have to complete that task and have to submit on the Moodle. So that's for today. From the other factors which we were discussing today. So hope you get the idea, and now form is open for the questions, right? So have a good day.